Okay, let's get started. Are there any questions?
Just to clarify about Wednesday's test, it's going to be the same length as the previous one, right?
By length, you mean number of questions? Yes.
Okay.
Yeah, it's still 5 questions, same as before. And just like before, actually, there are going to be 4 programming questions and 1 written-ish question.
Okay.
Yep. So it's the same pretty much as before. Other questions? Yeah.
Could you go over question 4 of the term example?
Gladly. So question 4 you said, right?
Yes.
Okay, so I'm not going to do a complete solution, but for interest of time mainly, but and you can email me if you have questions. So we have to write this function merge. So this function actually comes up for a sorting algorithm. We won't talk about it, but there's a sorting algorithm called merge sort, which does mainly this operation within it. So you have 2 vectors or arrays or whatever, it doesn't matter. Both of them are sorted themselves. So these 2 examples right here, they are sorted. So we don't have to do anything to those. But I want to combine them together, put all of their values into one bucket, such that the resulting one itself is sorted. So if I just stick on the second vector to the end of the first one, it's not sorted, right? So we would actually need to be able to put them together. So I'm not asking you to write a sorting algorithm here. So you don't need to do that here. What would you do? Yeah.
Add the second one onto the first one and then just sort the combined one.
Yeah, but I'm not asking you to sort here. So like the test on Wednesday, you don't need to know sorting algorithms. So I'm assuming you don't know how to sort out vectors here. I'm asking you, how do you combine them? Well, look at these 2 vectors. Which element should I consider first of those 2 to put into this resulting vector first? Yeah, okay, so I should only look at the first place of both vectors. So the 1 and the 2 here. Which one of those 2 should I put? The first one, right, because the 1 is smaller than the 2, okay? So then I place the 1 into here. So the 1 is done now. 1 and done. What do I do now? Which 2 should I look at now? Well, should I still consider this 2 over here? Yeah, because I haven't added it yet. Should I still consider this 1 over here? No, so I should look at the 3 next. Which one of those 2 should I add? The 2, because it's the smaller of the 2. So then I add 2. So now I'm still looking at this 3, and now I'm looking at 6 over here. Which one should I add? 3, because 3 is smaller than 6. And if you carry on through, we get this exact thing. So what do you actually do? Well, you're going to have 2 indices which start at 0. So you're going to have one index that is corresponding to this vector right here, and one index for over here. So then you keep going while these indices are still valid. So whatever valid means, we keep going as long as there's something else to look at. Then, if that's true, I look at the values, this first index, in the first vector, and the second index in the second vector. Which one of the 2 should I add? The one that's lesser. So if this one over here is smaller, I'll add this one. If this one is smaller, I'll add this one. So let's just say that this one is smaller. The first one really is smaller. What else should I do to the index? After I add it. I should add 1 to it. And then try again. See if the indices are still valid. If they are, great. Then add the smaller of the 2. and whichever one is the smaller of the two, I move that index, whichever one it is. So that gets you most of the way. So here's an issue. What if we do this and the first index becomes invalid? We've exhausted the entire first vector, but we still have stuff in the second vector left to add. What should I do at the very end? Add all the rest of them, because this vector is sorted. So from wherever it is, the rest of the elements should go at the very end of the resulting vector. If the first one has stuff left in it, then I add everything in the first one. So if we just do pseudocode of this, so here's the idea. So I created two indices, idx1 and idx2, to set to 0. So while valid indices, so this is not real C++, obviously. So if value for idx1 is less than value for idx2, make this bigger. So that means I should add the value for index 1. So I should append value for idx1 onto resulting vector. And then what should I do with idx1 as a result of that? Increment it. So plus plus. And then otherwise, which index should I add? Which value should I add? idx2. Well, if they're equal, it doesn't matter which one I add. So I should append value for idx2 onto resulting vector. Oh, this should be idx1. And then here, idx2 should go up because I'm adding the thing in idx2, and then I'm okay there. Well, at the very end, after all that's done, either both of the indices are invalid or one of them is invalid. Whichever's the case, well, what I could do is just say, regardless of whether idx1 is still bad, I can just say, while it hasn't been exhausted yet, I just add everything in the first vector. So while idx1 is still valid, add value for idx1 to vector. And of course, increment idx1. Well, suppose that idx1 is invalid after this first part right here. So it really is exhausted. What about this loop? Will it ever be executed? If the first vector is completely done, there's nothing left in it to add, will this loop ever execute? No. So therefore, we're okay. If there is stuff left in it, then this will add everything we need anyway. And we do the exact same idea for idx2. And that's it. So the idea here is just to march along, moving one of the indices at a time, depending on which one is the smaller one of the two. Then at some point, either one of them must be exhausted or both, at which point, whichever is the case, I just add all the other ones, and then we're done.
And for checking validity, would the size of the vectors be known? Or?
Yeah, well, even if they're not known, you can just say dot size, and then you're done. So here, the valid indices for this one are what? The 4 vector right here. 0 through 3, and here it's 0 through 2. So while the indices are strictly less than the size of the vector, that's what validity means. So while the first index is less than 4 in that case, and then strictly less than 3 in the other case. Other questions about question 4? Yeah.
I know in just talking code-wise, specific code-wise, I know that when we were doing the previous lab that we just submitted, I had come across the swap function, which is to swap values within a certain array or something. But in this case, because you're swapping between 2 different sets of it,
You're not really swapping though, because I'm pushing back into this vector. So it's not like I'm looking into a value over here and a value over here and swapping them. I'm only taking the value over here and putting it over here.
And by just adding an increment on the previous one. That's in case for the size, right?
I'm not sure what you mean.
So whenever you had IDX1++,
Yeah.
is that a measure you're taking for the size of the index, or?
No. This is just an integer. That's all it is.
Oh, okay.
But it's an index into the vector. So while IDX1 is still a valid index in its own vector, that's what valid means.
Okay.
Yeah, but it's just a normal integer. It doesn't mean anything else. Other questions?
And also just in general,
Yeah.
if any last minute questions come up, are the solutions for these ever going to be uploaded for the test?
Well, I mean, no one's ever asked me, and I'm not sure if I would be able to by the test date. Is there another question you want to go over, or?
Oh no, just in case for like worst case scenario.
Yeah. Well, no one's asked, so. Other questions about the sample test? Oh, yeah.
Are you gonna post this the video usually? Are you gonna post that before?
Yeah, so I have office hours tomorrow, and I'll upload them then.
Okay, thanks.
I don't have a fast internet connection at home, but I do here. Thank you, Cox. Any other questions about the sample test? Okay, so I should mention one thing that I got a lot wrong last time. So I thought last time that the vector square bracket index operator checked the bounds of whether the index is actually valid, but it's actually not. But I thought there must be something a vector that does, and there is. So if you look at the functions, there are two ways to access an element. So we don't know what operator does, but that is the square bracket thing. There's an at function. So if you call .at and pass in the integer for the index that you want, that does do bounds checking. Whereas the square bracket operator does not do bounds checking. And the reason for this is they want to have vector be like an array such that the square bracket operator is super fast, but they also want a way to check whether the index is actually valid or not. And so they can't just change this because then it won't be as fast, because they have to then check the index if it's valid every single time you access. Whereas, so they want this one to be fast, but they want this one to be correct. So if you call .at something, maybe 3, then it will check whether 3 is a valid index or not. Whereas if you do square bracket 3, it won't do the check. So I got that wrong last time, and I wanted to correct the record. Okay, so last time we started talking about what? Searching and sorting, right. So what is the motivation? The motivation is we got a bunch of data now because we have vectors and arrays, and we want to find data inside of it. Maybe to make sense of the data, or to figure out maybe a distribution of the data, that sort of thing. So we noted 2 different types of search algorithms last time. One of them is linear search, which is just scan through all of the items in the list. Doesn't matter what the list is in any order. Just scan through the entire thing. If you find it, great, it's in there. If you don't find it, it's not in there. Super easy. But then we noted, well, if we have the list that being sorted, so the list is sorted in, say, ascending order, then what can you do? Well, what you can do is just say, look at the center element of the list, the one in the middle. If the element that you're looking for is less than this middle element, then Do I need to search the second half of the list? No, because the list is sorted. So that cuts out half the list immediately. So that gives us an inclination of why binary search is better and why we should care about sorting algorithms. Because if we just sort the list one time, then we can make our searches much faster because I can just do binary search every time. Whereas linear search, you can't assume anything about the data, so it's slower, but it works on more lists. So just an example of linear search we did last time. We wanted to search for the value 11, and it's not the first element, not the second, not the third, but we did find it on the fourth element we looked at. If we looked for the value 8 or 7, it doesn't matter, then I'll be scanning through all of these elements, and I won't find it. Because why? I won't find 7 because it's not in the list. It's not in any of the places in the list. Super easy. And it's actually really easy to write. So how would you write this? So let's just say you're looking for a value x in the list. What would you do?
Quality comparison?
We'll get to that. But what type of loop should you use? Yeah, for loop, or even better, range-based for loop. Yeah, because why? Do we care about the indices here? No, all we care about are the values. So just use a range-based for loop. For int element in the array or vector, what should I do? If I'm looking at a particular element in the array or vector to compare it with x, what should I do? If the element is equal to the thing we're searching for, x, then what do we know? It must be in there because one of them is equal to the value we're searching for. If it's not equal, does that mean that it's not in the list for this one particular element?
Oh, element. Okay.
So let's see. So let's just have this array right here. So let's have an integer x, cnrx, and then say for int lm in the array, well, vector here, doesn't matter. If the element that we're searching for is equal to the x that we are querying, is this actually in there? Then what should we say here? Is it in the list? More emphatically. Well, no, what does this indicate about the value x? Is it in the vector or not? It's in the vector because why? Because it's equal to the thing we're searching for. Okay, great. So see out in the vector. There's an issue with this. We'll come back to it. Then what if we get out to here? So like we searched through the entire list, we've never encountered this if statement right here. What should we do? Not in the vector. Great. Not in vector. And I'll put these on here to make it easier to read. Okay, what's the issue? What if I entered 84, for example, for x? What would happen?
It's still going to say not the vector after.
Ah, it won't say not. It will say not in vector here. What's an easy fix for this?
Return 0.
Yeah, return 0. Yeah, that's an easy fix. So I can say let's do G++ main. I gotta do the C++11 thing to make it work. A dot out. 84 is in the vector. I think 87 is? No, it isn't. Yeah, so 87 is not in here, so it prints not in vector. So what was that, like 5 lines? So pretty simple to write. Any questions about it, though? Yeah.
How does it exit? Okay, I guess it just goes through all 4 possibilities and then it exits the for loop.
Yeah, it exits the for loop if this if statement's never called, which means it comes down here. If we want to implement this as a function, you gotta do like a return true or false. So it depends on where you place it, but a return 0 works fine here. Other questions? Okay, so we talked about trade-offs last time. It's super easy to implement, and it could be in any order, but the disadvantage is it's slow. So if you had 100,000 elements, then you have to search on average half of the list because it could be in the first half or the second half. So, but regardless of that, you're going to be searching a lot of elements no matter what on average. So we talked about binary search, which is, well, the only assumption we're going to make is the list is sorted. Let's say in ascending order. Then I don't know where the value I'm looking for is. I just don't know. So to cut the most on average of the list away that I need to look at, I just look at the center element of the list. So if there are 100 elements in the list, then I'm going to look at index 50 because it's halfway in the list. Then whatever the case may be, the value I'm searching for is either the one I just looked at, great, we're done. Otherwise, it's less than the element we're looking at, or it's greater than the element we're looking at. If it's less than the element we just looked at, then do I need to consider the second half of the list? No, because we know the list is sorted. If we didn't know the list is sorted, can I make that assumption? No, because we don't know the list is sorted. So because it's sorted, we can know this. So then I cut the list to say, I'm only going to search between the beginning of the list and the middle element instead of the whole vector here. So I cut the list in half. And then I do the exact same search again. I look at the middle element of this now shorter list and do the either it's equal, less, or greater than comparison again. And then cut the list at half again, half again, half again, until we'll get to some stopping criterion, which is the stopping criterion is the range we're looking at is either exactly one element or the lower half of where we should look at is bigger than the second part, meaning that the range is invalid. But we'll see that eventually. So we just keep going until either we find it or we have this invalid criterion. And that's all we need to do. So let's, yeah, go ahead.
Could you choose to like stop the binary search once it got to a certain point and then switch to a linear search?
Yeah, great point. So could you say, do a hybrid of binary and linear search? I'm not sure what that would be called, but what you would do is you do this halving over and over and over until you get to a list that's small enough for some definition of small enough, and then you have some smallish list, and then just do a linear search over that. And that's actually a great point, and it's a great segue too. But I just want to do the example first before I show that, yeah.
With the binary search work, can like lists that are values entered, or like there's no middle, because like say value, say list of 8, list of 4, don't really have a middle, you have to keep breaking it down and down.
I'm not sure what no middle means.
Like, if you said binary, it finds like the middle value of a list.
Mhm.
But if it's like you have a list of like 8s, you would have 4 on one side, 4 on the other. It's not really a set.
No, it's the middle index, not middle value.
Okay.
So there's always a middle index. It may be equal to the largest value in the array. So it could be really skewed. All I care about is that the list is sorted, and I find the middle index, not middle value. When I said middle value, it says here value of the middle element. So it's the middle index here.
Or,
Yeah.
Is there any issues with, I think what he's talking about, if you had an even number of indices.
Yeah.
With
So.
no middle value.
Yeah, so if you, are you asking that?
Yeah.
So what you would do there is you would round down. That's the way that people usually do it, is compute what the middle would be. If it's like 0.5 is the supposed index, just round down. If you have like an imbalance of 1 on one side and less 1 on the other, then it doesn't really matter that much in the overall how long it runs. maybe you have like one more integer to look at, but one more of those versus 100,000 is much better. So it's not really a big deal here, but you always round down.
Are indices values, are they always integers?
Yes, indices are always integers.
So you could technically just divide by 2 and let it truncate it.
Yeah, that's what it's done.
Okay.
Yeah, so you would compute that's actually an interesting point for some other reason. So you compute, if I'm supposed to be looking from index I to index j, then the middle value is I plus j divided by 2. So, and then truncate as a result. Yeah. So here, there's a reason why they have an odd number of elements. So what you would do here is, well, what is the middle index here? The one corresponding to 11, yeah. So we would look at 11 first. No matter what the value we're searching is first, we look at the value 11 first. So let's just say we're searching for 11. Did we find it at our index that we're looking at? Yeah, because it's equal to the thing we're searching for. If we're looking for 7 and we look at 11, is 7 less than 11? I swear they did that example on purpose. 7, 11. Is it less than 11? Yeah. So should I search this second half of the list? No, because it's sorted. So should I search 11 again? No, because it's not equal to the thing we looked at. So the indices we look at now are the 0th index, which is the value 2, through the second index, which is 5. Sorry, index 2, which is 5 here. We don't include the thing that we just looked at. So if it's at index I for where 11 is, now we're looking from index 0 through I minus 1. Because we don't want to search the element that we know it's not equal to anymore. It could be the one next to it, but we don't know that for sure. But now I've made the list roughly half as big. Then we search the index here, 2 through 5. What's the middle index between 2 and 5? Or what is the value associated with it? 3. Good. So is 7 bigger or equal or less than 3? It's greater than 3. So should I look at 2 anymore? No, good. So now the way that you compute the index is it's from the middle value plus 1 for the index, and the high index stays the same because we're cutting off the first half of the list. So the 5, it could be right here, but it's not equal to 3. So I'm going to move the lower index from where 3 is 1 more. So now the lower index and the higher index are in the exact same place, which is at 5. So we search the value 5 now. So is it equal to 5 or greater or less than? It's greater than. So which one should I move because it's greater than? Should I move the lower index or should I move the higher index up? Lower index up because it's not in the first half of this list. So what happens is the lower index goes from where the middle value is, which is where this is, plus 1, meaning that the lower index goes from here to here. So is the lower index and the higher index a valid range now? No. So did we find 7? No. So that's a proof that 7 is not in this list because every value we searched, we didn't find it, and then eventually we had the lower index bigger than the higher index. I'll show code in a bit, but yeah.
So basically you could set the valid ranges that if your lower and higher index ever equal one another, then you can say that it's not a valid range.
Yeah, so that's another way to implement it. If the lower and higher index are the same and it's not right there at where they are, then it can't be in the list at that point. But every implementation that you'll ever see has the condition being while the smaller index is strictly less than the higher one. Actually, less than or equal to. Yeah, less than or equal to. Yeah. Other questions, just on the example? Okay, so some trade-offs. Well, since we cut the list in half every single time, what if you just go through analysis of how it works? I won't test you on this, I don't think. Yeah, I won't test you. But if you go through the analysis, what you find is that instead of searching roughly half of the elements in the list, you search roughly the logarithm of the number of elements in the list. Base 2, actually. So if you have 20,000 elements, on average, you'll search 15 entries of that array, which is significantly better than half of 20,000, which is 10,000. So that's obviously a good idea. Or is it? Vsauce moment right there. But you have to have the elements in order. Because even if one pair of elements are in the wrong order and everything else is sorted, I can't guarantee this. Because what if I search for one of those two? Then I might not be able to find the element I want. So it requires the array elements in order. But, okay, yeah. So let's actually investigate this claim a little bit. So it says it is much more efficient than linear search, right? So can you tell me the reasoning behind why that is stated like that? Why does that make sense?
Because it eliminates the necessity to search for every single indice.
Right. So whatever the list is, I cut the elements in half every single time. So by cutting half of the elements, I don't have to search the entire list every single time. So that's why it seems reasonable to suspect that it's much more efficient than linear search. Okay, does that make sense? How many of you think that that's a reasonable thing to say, that it's more efficient than linear search?
Probably a trick question.
Yeah, it actually kind of is. So let me show you a coding example I did last time I taught this class, but I'll share the code with you also. So I was not sure about that, so I wanted to actually time it myself to make sure whether this claim is true or not. So what I wanted to do was to say, I wanted to compare linear search and binary search. And in order to make the comparison fair, I needed to have the vector that was tested on both to both be sorted. So whatever the list is for linear and binary search, I want them to be exactly the same. And because computers are so fast, what I wanted to do instead was to, instead of just sorting one time, I wanted to sort it a whole bunch of times. No, sorry. Not sort it, search it. I wanted to search this thing many times to make sure I get rid of all weird things that might happen, so everything averages out okay. So let me run through what this code actually does. So here I'm going to say how many elements I want in the vector. So here it's 10,000 elements. And I wanted to be able to search it num runs number of times. So for linear search, I'm going to do linear search 10,000 times, and I'm going to do binary search 10,000 times, okay, to make the comparison fair. Then right here, all I do is, so you may not have seen this before, but basically what this does is it adds 10,000 random integers, completely random integers, to the vector. So it just adds a whole bunch of elements there. I perform sort right here. So you may not have seen this, but this is one way you can sort the vector. Then what happens is here, there's this awesome library called Chrono in the standard namespace, and it allows you to do precise timing. So if I wanted to time how long something takes, then Chrono is a way to go. So how do you actually use it? You call the now function, which says record how a certain value right now, and then I call now again once all the code I wanted to test is done. And then the difference in time is just the difference between those two values. And then here I'm recording nanoseconds. So how many nanoseconds does a linear search take? So in linear search, what I do is I'm just going to do a whole bunch of searches, the num runs number, and then I'm going to say, I'm going to generate a random integer and search for it. And then I'm just going to call std find, which does linear search. So it just does normal linear search, and it searches for rand inside this vector. Super easy. And then it reports how many nanoseconds linear search took for those 10,000 trials. And then I do the exact same thing, except now I call binary search. So it does binary search for a random integer in the same vector. So, and then it reports how long it took. So let's actually run this. So let's see, where is it? So, and one other thing. So the C++11 is just to make the auto work. The O3 here is to make it so that the algorithms themselves run as fast as possible. So it performs all possible optimizations that could be reasonable for these two vectors. So each one of the two gets as much of an advantage as possible. So let's actually run it. So it seems to hold true. So this says linear search takes 39 I think million nanoseconds, whereas binary search takes 550,000. Okay, so 39 million versus 550,000. So what can you conclude from this? Is it always faster? So this is something that happens a lot. You see it on TV or anywhere. I point to one statistic and then I ask you, what is the conclusion what you can draw from it? Can you draw anything from this? No. What could you conclude from this? In this instance, it's faster by quite a bit, actually. But does that mean it's always faster?
I'd be curious if you changed that number to 10.
That's the exact number I was going to consider.
Yeah.
Can anyone explain that?
It's more processing power to do the halving of 10, because you do 10 divided by 2 would be 5, divided by 2 is 2.5. So it's doing more calculations in order to do the binary search.
Possibly. But there are other factors that may occur. So I just want you to be able to take from this that just because a claim like this exists, and it's from a big publisher company with a big textbook and it says it is faster, is it always faster? No, even on the same list. So be very careful when you see claims like that, because it's not always true. So why did we actually see this? So I won't go into the exact reasons because it's kind of complicated, but one of the reasons is when you say, I want to access index I into this vector, what actually happens is it doesn't take it from main memory and puts it in your CPU and works with it. How many of you heard of the cache hierarchy? Okay, so a few. So what happens is, well, if you're accessing index I, is it really likely you're going to access index I plus 1 or index minus 1? It seems that could be likely. So in your computer, there's something called a branch predictor. And what happens is it tries to predict your access patterns of data. If you're accessing things in a linear order like this, then what happens is it takes a whole chunk of memory at once, because that takes the same amount of time as accessing one thing from memory. So it takes a whole bunch of stuff and puts it into your caches. Caches are much faster to access than main memory. So that's one reason why we're seeing such a noticeable improvement with linear search, because the number of integers in these vectors is small enough to where the cache performance outweighs the fact that binary does fewer comparisons. Binary search always does fewer comparisons. That is true because we're cutting half the list every time. But linear search is faster because you're accessing things in a linear order. Whereas for binary search, you're jumping all over the place and not accessing things in a linear order. So that's why we're seeing a huge advantage there. But if we go back to what we had before, compile and run, then the differences are going to change. So differences are going to change. Great quotes from Ryan. This is why we see the noticeable improvement with binary here. Because as the list gets really long, the effect of having to search through everything is going to outweigh the fact that binary search does very few comparisons comparatively. So just be careful. With small lists, it could be that one algorithm is faster. With long lists, it could be the complete opposite. So when you're asked, maybe like in a job where you're doing programming, and you are trying to weigh whether we should use algorithm A or algorithm B, and you know from whatever that, say, algorithm B does fewer comparisons overall than A, always. Which one of the two should we use? Should we always use B? No. So if you make some assumptions about your data, maybe the lists are small, then maybe algorithm A might be better, or algorithm B might be better. What's a way that what should you do to verify one's better than the other? Test it. Test it yourself. Do timing of your code. So this is something called profiling. So not other kinds of profiling, timing profiling. So here you're going to profile how long your code actually takes. And in fact, last time I taught this class, assignment 7 actually was testing how long the sorting algorithms take, not the search, the sorting algorithms take. And see, for small lists versus long lists, do we see that one algorithm is faster than the other? And in some cases, we saw that the naive algorithm was faster because it does cache performance much better. So, yeah.
Is there any effect on the size of each indices? So if you're searching each indice is incredibly large, would this comparison change?
Excellent question. So the question was, well, what if we had the values in the indices taking up a lot of memory? So this gets into a huge issue. So called dynamic memory allocation. So think of vector, for instance. So vector doesn't actually create arrays in the way that we have done it so far. So what we've done is we had int square bracket array equals values, or array of 4, which declares 4 integers. That is something called stack memory. And stack memory is faster than this thing called dynamic memory. But the issue is, what if you wanted to have this array that we are declaring to have any size you want instead of a fixed size? That's something you need to use dynamic memory allocation. And the issue with that is, if you have each one of these elements inside your vector requiring dynamic memory, then what happens is if you access index right here, then you're going to have to jump to wherever the dynamic memory is allocated and come back, invalidating all of the cache benefits. So profiling when you should have dynamic memory versus not, which we'll get to eventually, is something that's really important. We were okay here because the values in the vectors here are stack allocated, so they have no dynamic memory. Whereas if we did have dynamic memory, then the results can be completely different. So or maybe in that case, because you have this cache invalidator thing, it may be the case that linear is always slower. I don't know the answer to this. But just be careful when you see claims like that. Other questions? Okay. Yeah, so just be careful when you see claims like this. But for long lists, yeah, binary search is faster, definitely. So you don't have to have just an array of integers. You can have an array of objects. So if you have like an array or vector of student objects, and maybe you want to find someone with a particular ID, then what you could do is say, well, how should I order the elements in my vector? Should I sort them by their name, or should I sort them by ID? Should I sort them by ID before I do the ID search, or should I order them differently? Because if I order them by ID, it might not be the case that they're sorted by name anymore. So maybe they were sorted by name, and then sorting by ID invalidated everything about that. So you have to be a little bit careful about like what you want the array to be sorted by. If you're curious how, say, Excel does sorting. So in Excel, what happens is, let's say we sort by one column, and then I say after that, sort by this column. What do you notice sometimes? Well, we sorted by the second column. The first one, relative to the elements in the second column, the first column still is sorted. So that is something called stable sort. So you have to be able to think, what type of sort do we want? Do we just want to sort blindly, or do we want to actually have it be a stable sort? Keep the order that it originally had and sort by this other field. So you just have to be a little bit careful here. Okay, so let's start talking about sorting. Because for binary search to be very powerful, we gotta sort algorithms. We gotta have sort algorithms. So what is a sort? A sort is, we got a bunch of values, put them in an order. Nothing more complicated than that. But you could have different types of sorting algorithms. So you could just say, I'm gonna sort alphabetically. Or you could do ascending numerically, descending numerically. You can sort by the length first and then say alphabetical after that. That's called lexicographic sorting. You can sort by a particular field of object, so maybe sort by ID and ignore everything else, or anything really. So you have to know ahead of time what type of sort you want. But let's just say we have some order where the less than symbol means the order that we want. So if I compare two things, then if this thing really is less than this, then by saying this less than symbol, the other thing, we get the true answer. So we're going to talk about two algorithms for sorting, which are called bubble and selection sort. So bubble sort, so I'm not going to go over everything now, but the idea is we have some things in this vector. Instead of thinking it horizontally, think it vertically. So here in bubble sort, we want the small bubbles to float to the top and the heavy bubbles to float to the bottom or sink to the bottom, as the case may be. So if we have a light element, meaning it has a small value, then I'm going to incrementally move it up the ladder until it gets to the place where it needs to go. If we have a heavy element with a high value, I'm going to have it fall down incrementally until it finds the place where it needs to go. Then if I make a pass over the vector and I find that everything is in the right order, everything adjacent is in the right order, then the whole thing is in sorted order. But if there's something that's out of order, then I need to float things down or make things sink, as the case may be. So I'll see you all on Wednesday.